These are the video notes for lesson 1.2. Before we get into 1.2, we're just going to do a real brief recap of 1.1, the introduction to recursive sequences. So we've got a couple different sequences here. And the thing we want to figure out is our recap is arithmetic, geometric, or neither. Again, what I said you could do is just try to look, and if you can just tell by looking, great. But if you can't tell by looking, then the way to do this by calculation is work your way backwards through the sequence. So when we do arithmetic, the numbers are getting bigger, so it looks like we're adding something. But if we want to check out what the common difference is, we actually subtract our way backwards through, and subtracting it backwards through looks like this. So I'm going reverse through the sequence, and then I subtract them in pairs, and you notice that it's common because I'm getting the same number every time, which means the common difference is 7. Now, I think probably most of us could just look at it and go, well, I'm adding 7, adding 7, adding 7. So that may be not that hard to figure out just by looking, but here's your backup in case the numbers are kind of large and you're not really sure. I also tried the common ratio, which would be dividing my way backwards, and what happened here is I divided in pairs going backwards. I did not get the same number, which tells me it's not a common ratio, it's not geometric. So if you were just kind of blindly trying, you'd have to probably go both and see which one produces the common number. So now I know it's arithmetic, and I can go ahead and write my formula. So remember, when you're writing recursive rules, it's not just about writing the use of n, what's going on with the previous term, but also always include the starter term. So again, if I pass this information off to somebody else, they would know 12 is where I start, and here's what I do to get the rest of the list. So always include that. Now look at this one again as a, is it arithmetic or geometric or neither? It looks pretty easy to tell that I'm multiplying by 4. So I don't know that this would be necessary, but just to show you again, so here's me saying I don't really know which one it is at all by looking, and I'm subtracting my way backwards through the sequence because these three numbers are different. I know it's not common, so there we go. If I divide my way backwards in pairs, so starting at 192 and going backwards, divide, I get 4. That is common, it's a common ratio. So subtraction going backwards will tell me common difference. Division going backwards will tell me common ratio. So now I know what I'm doing is going forward, multiplying by 4. So I know it's geometric because of the multiplication. My first term is 3, and it's 4 times the previous term. Again, keep stating that first term as part of your answer when you're writing recursive formulas or rules. Now, as I look at this one, I don't see a pattern of addition. So let's say I tried to add 2, but then adding 2 here doesn't work. Let's say I tried to multiply 2, but then multiplying by 2 here doesn't work. So now I feel this fits into the neither category. What I do see going on, remember neither means you got to get a little creative, but I think I see a pattern that does something like this. If I square the number, the previous number, it produces the next one. So 2 squared is 4 squared is 16. 16 squared is 256, and all of a sudden, I think I see my pattern and I got it. So my first term, starter term, is 2, and then how I write that is the previous term squared. So in other words, to get 4, I have to square 2, the number that came before it. To get 16, I got to square 4, the number that came before it. So I think arithmetic, geometric, usually pretty easy to see. Neithers, you kind of can tell with a little bit of trial and error it's not, but then the hard part is, what is it actually? And then this is your backup. You know, if it's not clear by just looking at the numbers, then here's how you check to see which one of these things is going on. Okay, good to do a little bit of recap before moving to today's material. Today really what we're doing is modeling growth and decay. So we're just taking the idea of sequences where the numbers in the sequence are getting bigger, or the numbers in the sequence are getting smaller, and modeling means look at an application of that. So growth and decay usually will be geometric because you're multiplying by a number to increase the size, increase the value, increase or decrease decay. And so what we want to do then is talk about what those look like as a growth and decay model. It's some pretty simple ideas. Here's some growth concepts, here's some decay concepts. A lot of times it has to do with value, so you can gain value, not just lose value, but cars pretty typically lose their value. Populations tend to grow, bacteria tend to grow, mosquitoes in Minnesota, depending on the weather, right? All right, let's get into it. So the first thing to do is understand which common ratio produces a growth or decay. And I think this is kind of easy to think about. If your common ratio is a number bigger than 1, like 1.5, well then clearly that multiplying by 1.5 is going to increase the number that came before it. That would be a growth. If your common ratio is something between 0 and 1, so let's say it's like 0.5, well if you multiply the number times 0.5 or half, it's going to get smaller, so that's a decay. So these tend to be decimals, and so do these. We'll talk about that in a second. Usually it's a percentage kind of idea, so we're going to relate a percentage to a rate to a common ratio. But again, geometric because we're using multiplication, so there's our geometric rule, common ratio times the previous term. So remember in the 1.1 recap, we said the correct way to find a common ratio is actually to divide your way backwards through the sequence using pairs of terms. That may come in handy as we start looking at some of the next set of problems, because maybe our numbers are starting to get big enough or we got decimals and it's not going to be clear to us what the common ratio is. So then by dividing, we can take care of that. So let's get into a problem and talk about growth and decay. Typically your growth and decay in a problem is going to be based on a percentage. And one of the things we have to do is percent change how that's different than a common ratio. And it's pretty simple. For example, let's say terms generated by these are going up. So clearly we're multiplying by something bigger than a 1. We're going to figure out what that decimal is, and then I'll talk about the difference between a percentage change and a common ratio. But for starters, we're going to stick to this. So as I look at these numbers, again, just kind of going from one to the next, it may not be clear, especially with the decimal, what it is. So the way we're going to do it is go in pairs and divide our way backwards through the sequence. So in pairs, I'm working my way backwards. Now, what I notice as I do that is I'm getting the same value. There's the common idea, and it's a ratio because we're talking about it being geometric. So what I can do for starters is talk about what's my first term, 16, common ratio, and create just your standard geometric sequence rule or formula rule. But then let's break down what the 1.25 is. So the 1.25 is your R, right? So when you do that division going backwards, you are clearly finding an R. So what is the percentage change? Well, the percentage change is actually the 0.25. So in other words, there's a 25% increase from 16 to 20, 20 to 25, and so on. That's a percent change. And so when you look at your R and you know that it's a growth, basically, then you can go 1 plus what? Well, there's your P, 0.25. So 25% increase or growth. So I know it's in a growth, it's pretty easy to tell because the numbers are getting bigger. So clearly we've got a growth going on. And this number also tells me it's a growth. Remembering that from earlier on. So that's how we determine the difference between a common ratio and a percentage change, and I'll talk about that again in some of the other problems. This next one, we're going to attack it again as the same idea. One thing we're going to introduce here is that typically first term in a sequence is called use of 1, but when we start talking about the value of objects, so if it's a car, a home, whatever, your iPhone, we talk about it as use of 0 being the starter term because there's no change, it's what you paid for it. So it usually takes time for that value to change. So we look at our common ratio or percentage change as time has to pass before the change happens. So typically when you talk about dollar amounts or the value of any kind of object, the starter term is called use of 0, and then time passes and something happens and the value changes. So as a scenario for this one, I think the numbers which I talked about with you guys in class kind of to me sort of match the idea of maybe buying like a used car and it loses value over time. So as the numbers go down, to me clearly it's a decay. And then we'll talk about, what's the decay rate, the percentage change. Again, the way to work this is go backwards through the sequence and divide, which will help you figure out what your common ratio is. With these numbers out here, maybe you couldn't tell. Here I probably could tell. If I went 8,800 divided by 10,000, cross off a few zeros, you got 88 over 100, and there's 0.88. So that I probably could have figured out. But, just as a backup again, to find that common ratio, divide your way backwards through the sequence. And it should come out to be the same. That's, again, how you know you've got a common ratio. So my starter term is 10,000. That was the value of, let's say, a car in this instance, and 0.88. Now, again, because that common ratio is less than 1, that also points out the fact that it's a decay to me. But what's the percentage change? Well, to get the percentage change, you would have to do 1 minus. So the idea here is, so I think what could be a little bit confusing about this one compared to the last one is the 0.88. You're kind of tempted to want to throw 0.88 in here, but that's actually not what's going on. Remember, 0.88 is actually R. So if you think about how you'd get 0.88, 1 minus what percentage decrease would produce 0.88. So think of 0.88 as sitting over here. Well, for that to happen, you have to subtract off 0.12. So 1 minus 0.12 is 0.88. In other words, this is what the value of the car, this is the value that the car maintains. It keeps as we go from year to year. But if I said, what's its percentage change? You'd say, well, the decay is I'm losing 12% in value every year. This is actually what it maintains, which is the common ratio. So when you're looking at this as your R, you got to sort of think about it as, okay, what's going on over here? And the last problem, I kind of put that in here too, but I was talking about 1, what did I add, right? And so in that case, since I had found R to be 1 point, I had already added the percentage in there. In this case, I'm saying R sits here. I think you could just reason it out. I think you don't need to get hung up on these little mini formulas. Just think about it for a second. If the car maintains 88% of its value, then it loses or decays by 12% per year. And then all of a sudden trying to plug into some formula isn't necessary. Just sort of reason it out to yourself. Okay, let's keep going here and go through about a couple more problems and we'll wrap it up. So, now looking at, again, an object, right? So we're talking about a rare painting, $150,000 value. The value of the painting is going to increase at 5% per year. Anytime you see anything that talked about as a percentage increase or decrease, that's definitely a P. We're talking about growth. So if it's growth, then 1 plus P would produce my R. In other words, 1.05 is going to be my growth rate. So there's something else to think about. But anyway, let's get started with initial amount and 1.05. Remember, I need the 1. What the 1 does, it brings along the actual 150,000. The 0.05 brings along the increase, and then just by making one number out of it, it actually does both those things for you at the same time. So growth because value bigger than 1. Okay, so start out with my initial value. Now time has to pass. So if we're looking at after 5 years, that means you have to go a year. So here's how this works. This is the initial value. A year passes. Here's the value after 1 year has passed. And to get that, I'm using my formula. So 1.05 times the previous term. Another year passes. Then another calculation happens, and it produces the next value. So here's the value after 2 years. And then, you can just keep this pattern going, so on down the line. So in 5 years, actually a pretty good percent increase in value. And that's really simple recursive formula right there. So geometric multiplying by a common ratio, and it's a growth, number bigger than 1. Okay, one more to go and we'll wrap it up. So this problem's got a little bit more going on because we're talking about an investment, and I think this is a little bit hard to understand because you guys don't have experience probably with a lot of investment so much. But if you do, great. Maybe this will make a little more sense to you, but I'll try to lay it out for you guys. $500 deposit. So in this case, $500 are going in. 8%, that's an 8% increase. When you're talking about gaining interest, you're going to increase your investment. So there's the 1 point again. 1 brings along the 500, and 0.08 brings along the increase. So in other words, my 0.08 actually from 500 to 540 produced the $40, and the 500 came with. And so on down the line. Interest paid once per year, so this is called annual interest. So that means it'll be calculated at the end of the year. So that $500 is put in, the year passes, and then the calculation happens here. I didn't call it use of 0 here. Didn't call it really use of 1 either, just sort of laid out the terms. So in this case, we're just saying the first year you put the money in, the $500 sits there for the first year. And then that year passes, calculation happens, and now here we go in the second year. So what makes the number of calculations change is the compounding, how often you calculate interest. So if interest is paid once per year, which is called annual interest, then I'm just going to do the calculation at the end of each year, just one time. If it's semi-annually, that means the calculation is actually done twice a year. But you don't get the 8% twice, because if I calculate 8% here and 8% here, you get 16%, and the bank's not going to give you that. They're going to give you just 8% over that 1 year each time. So what happens is you got to take your interest rate and divide it by how often you get the calculation to happen. So 0.08 divided by 2, 0.04. My new R is 1.04. And now what happens is I get 1.04 twice a year, semi-annually, and then over the course of that year, I still got my 8% going on. Now, as far as calculation goes, just continue the pattern. Right? You can go times 1.04 all the way through. It's just the idea is you're getting 2 calculations a year as opposed to 1 calculation a year. And that should be better. More times you calculate interest, the better off you are, and compare the two numbers. You're doing a little bit better in this scenario than you are in this scenario. And then even better is quarterly. So what I'd have to do there is take my interest rate, divide it by 4, because quarterly is 4 times a year. 0.02. Now that means every year has 4 calculations, so I will get it calculated 4 times a year. Still start with 500 times 1.02, and then just continue the pattern on. So this actually is 1 year has passed, and along the way, every quarter of the year, a new calculation happened. But again, you're going to get 2%, 2%, 2%, 2% for a total of 8%. You're not going to get 8, 8, 8, and 8. So whatever your percentage is, it's got to be divided equally based on what this number is, quarterly 4 times a year, semi-annually twice a year. Then just continue the pattern, just let it run. So again, if you compare the last number here to the last number here to the last number here, you notice that quarterly is better, and it should be, because you're getting more calculations happening in a year. Okay, that's going to wrap it up for our 1.2 modeling growth and decay. with a geometric sequence.